fourth polynomials. And after they did that, like, what about x to the fifth? You probably just keep going. And then there was a proof a few years later that you actually can't solve the quadratic equation, or kinetic equation. Boltzmann was a physicist, of course, he's Boltzmann constant, very famous physicist for his laws of, I don't remember what he did, I don't know much about physics. De Moivre, I don't remember how to pronounce it. I had a French teacher who told me how to pronounce it, I can't remember. Please excuse my French. Teksinski, purely theoretical, just stuff that I don't care about, no one really cares about. But at the time, when he was defending his dissertation for his PhD, one of the smartest mathematicians in his subject at the time had such profound interest. He's such a smart mathematician, he's so dedicated, his work is so profound and amazing. And it was totally obscure stuff that you would never actually care about, no one actually does care about. It's just for the sake of completeness, and he had great solutions for it. Newton was kind of a nut job, but everyone knows Newton was kind of a nut job. Newton did lots of stuff, like calculus, even though Newton's work was just based on Fermat's work. So a lot of Newton's work is original, but a lot of it isn't. A lot of mathematics has been repeated, like Pascal's triangle. So there was a Chinese and an Arabic. There's two different Chinese and Arabic mathematicians who discovered Pascal's triangle before Pascal. And then after Pascal, before Pascal, like 20 years before, I believe Tartaglia actually had created his own called Tartaglia's triangle because he was also an egotistical bastard. So Tartaglia came across Pascal's triangle before Pascal. But I mean, Pascal wasn't even the first anyways. But Pascal, of course, gets credit for it. Because why not? John Nash, his work was very wide range, not necessarily theoretical. Paul Erdős, who I've missed this entire lecture, is a man who I couldn't begin to talk about. I'd love to. I'll do it. There's a really good tale at a university in Florida about a teacher named Aaron Meyerowitz. And one day, Paul Erdős, it's pronounced Erdős, in case everyone thinks I'm really weird for pronouncing it right, and not wrong, like Erdős. It is Erdős. Aaron Meyerowitz came to the airport to pick up Mr. Erdős, and he said, okay, here's the map, can you direct me to the conference? And everyone had to drive him around, and you couldn't even read a map. Like, Paul Erdős would literally just do math all the time. Like, he was so good at it that he would sit down for 2 weeks, try to brainstorm, and they'd solve something, and he'd leave. And that was what he did. And he was really good at logic, which made him end up, I think, in an insane asylum. That is how most mathematicians live. Most of their work they don't expect until they die. Except for, I think, like Euler, who, like, he had a pretty good life. He had 2 kids. He was the father of 13 kids, of which 8 of them didn't make their infancy. And he raised all 5 kids by himself. Well, not by himself, but with his wife, and he was blind, and he taught them all math. And his later years, I think they said his last day of his life, he taught the kids some math, and then he had a brain hemorrhage. And he literally said, I'm dying. Like, I guess he knew that he said, I'm dying, and then that was the day he died. And basically from there on out, like, his work was published for the next 50 years. Like, they never stopped publishing the works. He has so much work to do. So much work that he had already done. And, like, it took forever. Like, he was recognized through his entire life, basically, for his math. So he's the only one who didn't really die, live a terrible life. A lot of people live really unfortunate lives.
Gauss seemed to have his shit together.
Gauss definitely had his shit together. Gauss was, basically everyone looked up to Gauss. They were like, yo, if Gauss says it goes, if Gauss says it goes, we follow, we listen. Like, if he could say, like, I want to give a doctor to this homeless guy, they would do it. Because they don't want to argue with Gauss. Gauss knows what he's talking about. Except for that one time that, of course, Gauss couldn't prove something. And Eisenstein, this guy showed up at 20 years old, he's like, it's just that easy. And everyone's like, oh, of course. It just works out. And I forget why I have Sophus Lee listed here, but I'm sure that he had something really weird that he did or something. The Lee groups are very strange anyways, I don't know anything about them,
So can you name any theoretical breakthroughs in mathematics that wound up being useful and or applied over the past 50 or 60 years?
Yes, okay, so Alexander Rosendiek worked on category theory. And if you ever used Haskell, you can probably talk about category theory, monads, monoids, monad groups, all of the nonsense that I don't care about, that most people don't care about unless they program in Haskell. He basically took category theory to another level. He talked about schemes and stacks. And like, if you go to the Wikipedia page for stacks, you're probably going to cry. The first 5 words don't make any sense. In fact, I'll just do it just for the hell of it. Cool, nice spelling. A stack, in mathematics, a stack or a two-sheaf is roughly speaking a sheaf that takes values in categories rather than sets. Stacks are used to formalize some of the main constructions of descent theory and construct the moduli stacks to define moduli spaces that do not exist. Okay, I don't know. He worked on that. I don't know what any of it means.
I don't know, it's sheep, right?
What?
There's a sheep.
A sheaf, yeah, what's a sheaf? I don't know what a sheaf is, I don't know. We can look at the page for a sheaf too and we can see what that means.
This is how you descend to the dark hole that is your bed.
Yeah, basically. In mathematics, a sheaf is a tool to systematically track and locally find data attached to open sets of topological. I'm done, okay. The point is that category theory ends up becoming really useful for quantum mechanics. And quantum, most of the quantum theory and stuff like that has like a really nice attachment to category theory. You can explain a lot of it with category theory really nicely, really smoothly. And it was weird because people were like really into category theory, they're really into monads and talk about what monads are and whatever that is. And because no one can really explain to you what a monad is correctly because it just won't make sense. Because there's no good definition for it. You can, anyways, one day a few mathematicians were like, by the way, category theory kind of makes sense. I think we have a good grasp on this. And they kept going and kept talking about it. And then the guy came on and was like, I know quantum mechanics, let's talk about that. And they're like, wow, that actually kind of lines up. This kind of works. So when you actually learn a lot of higher order category theory, you actually know how quantum mechanics works without knowing anything about quantum mechanics. So you can sit in a quantum mechanics lecture and you can basically connect the dots as much as you want. And like, it's really cool because you know the internal of quantum mechanics without knowing anything about physics or high energy particles or anything like that. So that was a really cool result that he had come across many years before we even talked about high energy particle physics and whatever that nonsense is. Or high energy physics, HEP, I don't know. Don't ask me about it. All right. Any other questions?
I mean, how useful is quantum mechanics?
I'd say it's pretty cool. It's pretty cool stuff. It's pretty
It's cool.
It's great for LEDs. That's how you make LEDs, is because of quantum mechanics.
That's
Sorry.
the important thing I can think of.
Throwing that out there.
I mean, it's good if you want to explain how things work. That's if quantum mechanics actually does agree with our system, which we don't have a full understanding if it does yet, because we can't really test a lot of it yet. We've tested some of it, we've been testing some of it, but I'm sure there is some quantum mechanics that is applied quantum mechanics where we do use it in daily life by some means that we don't know about.
Quantum computers. I mean,
Those are even real. I don't know.
they're very important.
I don't even know if they're real though.
They're like this big and the cooler's the size of a refrigerator.
All that helium we're missing from like the atmosphere and all
It's literally the same
spent
active quantum
cooling.
I mean, we don't really know if those work or if they're real quantum computers.
Who knows?
No, there is a quantum computer. It's only
D-Wave has
very,
said there
very
is.
small.
Oh yeah, D-Wave has like a 5. It is like a metric for a unit qubit. It's a qubit, yeah, like a 5 qubit or 500 qubit computer.
But the only confirming quantum computer is Fujio.
Yeah, so I don't actually know how well they work if we can use
It
them.
doesn't work very well.
Exactly, it's just too complicated for us.
Really, the only like very good use of quantum computer is for breaking encryptions, and you need a
Wait, we have Shor's algorithm, which is nice. But I mean, then there's SHA-3, which is safe against quantum attacks.
yeah.
So this is kind of a vacuum of
Acronym.
Wait, what did I do? What did I say?
Oh, I got a little of it. I just like.
SHA-3, I'm sure you know
No,
SHA-3.
I know exactly what it's just funny.
Shor's algorithm is a quantum algorithm that cracks basically like
Encryption, it's encryption speed.
the word is integer factorization problems much faster than we can do them in normal computers because you have 3 different states now, or no, not 3 different states, but you have 3 different states instead of just one state on and off. Yeah, it's just a really lot of. Alan Rosnick didn't know anything about it, but he was really good at what he did. That it actually works. It makes sense somehow. It could be coincidence. It could probably.